Welcome to our second lecture of data analytics. Today we'll be covering stuff that we haven't finished last time and build upon that. Today we'll try to understand what is all this Bayesian thing about. Hopefully it will be understandable. So let's move to Bayesian stuff. What is general idea of Bayesian statistical modeling? And Bayesian statistical modeling works on main idea that we have to do this stuff that we discussed before about statistical modeling, data generating process, uncertainty, but Bayesian data analysis gives us, let's say, a language that we can work with. Give us tools that allow us to represent all these very nice round things that we're working. And generally, there are three essential steps that might be repeated ad nauseum. First, we specify the full probability model. That is the model that represents how the data what is the phenomena of interest, how it is being influenced by outside factors, how we are able to measure that phenomena, how we are able to measure these outside factors, because it's not always the situation that when we have independent variables, those independent variables are what actually influences the process. It might be some kind of observable thing about those factors that are we can, for example, when we want to observe the influence of the climate on certain process, we can only use temperature measurements or some kind of humidity measurements. But those are not the climate; they are symptoms of the climate, right? So we can only observe. So all those relationships have to be included in our model that corresponds to a situation, how the data is being generated by it, knowing the parameters and inputs. Then, using the observed data, we try to condition our model of the observed data in order to be able to infer about knowing what we know about the data, what data is possible, generally, using the framework of model structure that we created, and using this information, what are the ranges of parameters that we have. So we want to, observing the data now, we know, let's say, we created the laws of governing our data generation process. Then we focus on observed sample that we had. So the sample that the measurements that we've obtained of variables that are available to us. And then we want to use this information in order to see how our probabilistic model conditioned on this new data. So this is a conditional probability distribution. If someone remembers something that happens in the first year of your studies, then we get this conditional probability distribution that gives us how actual data would look like to be consistent with what we observed, what kind of parameter values are consistent with what we observed. And then, having this conditional probability distribution, we can now check and evaluate our model. So this new distribution that incorporates our prior knowledge, so our probability model, and our data is called posterior probability distribution, which comes from the Latin a posteriori. And this posterior distribution, we can now check, does it represent what we really want? So, does it generate the data that is consistent with what we can observe? Doesn't it generate something that is logically consistent with what we observe. For example, doesn't it generate, say, negative values of water level, which can happen. For example, your colleagues, when they are doing certain experiments on water tank systems, create a model, and they don't seem to be bothered when, for example, in the model, the water level drops below 0, which corresponds to there's a negative water inside them. So this is something that is one of the checks. So you do multiple kinds of check of your models. You check this is consistent, you use some kind of metrics that represent the, perhaps using test data, perhaps using some kind of predictions of out-of-sample behavior, or just eyeballing it. And remember, will be returning here, human mind's assessment of model operation is a very important tool. The way we can look, for example, on the is histogram of simulated data consistent with the observed data is something that will be difficult to quantify, to give the computer to what is similar or not, and we can clearly see what is not going on. Especially we can determine, oh, for example, our model generates too many zeros. When you have a model that's, let's say, model the number of resets of device in certain period, it generates too many zeros because all those devices, let's say, should have at least, or we observed, at all have at least one reset per week, just for natural rebooting, and the model doesn't generate it, so too many zeros. And for computer, it will be very difficult to assess that this is the problem. And when human looks at the histogram, say, okay, those two are not consistent. And comparison of actual numerical value is not that relevant because, again, we work with uncertainty. We work with probable realizations. So the fact that actual numbers are different is not the problem. But if we can see the trend and tendency, we see that something is wrong. And as aspect of changing our model, we really need to put only this information. It's wrong, or it's good. It's better than the previous one. What can we then see? What we can add to the model to compensate for certain aspects? So human evaluation is very important. So after evaluating how our model works, we either accept it or we move back and test it and test it and test it until. So we start with usually we start with simple model and we add to it. More rarely, we start a big model and we try to some kind of subtract from it because this is the more difficult situation. And we are talking about Bayesian statistical modeling. And Bayesian statistical modeling generally is the situation when we incorporate previous knowledge in order to make predictions about what's going on. Here's the XKCD comic about the general comparison between frequentist and Bayesian approaches, because in frequentist approach, the data is only thing we have. So if we have a detector that is being used to measure neutrinos and explain does our sun exploded, right? So it can verify if our sun is a supernova. And having data from this detector and using classical frequentist data, we can compute the test statistic that's using p-values and certain other things, we can conclude like the sun has exploded. However, still, we are standing here next to the detector, which should detect our sun, the supernova, which generally, if light approaches sun, light from sun approaches Earth, it means probably would be some kind of detectable by a person standing on Earth. if sun was supernova or not. So generally, Bayesian statistics incorporates multiple other stuff and works in a bit different ways. Because there are few main differences. In classical statistics, which generally represents probability as having a sequence of events, how many times in this sequence certain event happened. That's why we talk about frequency. How many times it happens to all possible situations. And in case of Bayesian statistics, probability is a measure of uncertainty, how likely certain event is going to happen. So, in case of frequentist statistics, we need to repeat event occurrences to be able to get some kind of information about it. In case of Bayesian statistics, we can assign probabilities to things that haven't happened yet. That's the significant difference. Moreover, in case of frequency statistics, when we want to use the mathematical tooling of frequency statistics, we assume that our data that we have is just a random instance of a process, and we are interested about a model that is as one true value that generated this model, and we generally observe the instance. So we are thinking about how reliable our model is, assuming that we will change the data that we don't have. Our model has the certain value, certain vector of parameters that corresponds to its behavior, is one fixed model, and we just are uncertain about what we observed, and we are interested how, in a sequence of random realizations of the process, so imaginary results of multiple data sets from the same experiment, we can infer about it. In case of Bayesian statistics, we have the data that we have. The data happened. However, our parameters are not one vector of parameters or one number. There is a probability distribution of parameters. In precise, conditional probability distribution that is conditioned on the data. So, how likely parameters are supposed to lie in certain areas of possible space, knowing that we observe this kind of data. So, this is a fundamental difference that in case of frequentist, data varies, parameters are fixed. In case of Bayesian, the data is fixed because we obtain the data, and it's only things that is really fixed that we really know about, because this is something that we measured with one or more or less faulty mechanism, but that's irrelevant. But what we know about the parameters is very uncertain. The parameters are not varying per se, but they are, our knowledge about them is very uncertain. So we do not know more. Second thing, in case of frequentist models, we can only rely on the data that is available to us. So we can represent only data based on the experiment that we performed. In Bayesian statistics, we can assign certain probability to certain things happening, or parameters relying in certain areas, and stuff like that. Why is this difference? Because in frequentist statistics, they decided that it is not possible to objectively assign the probability, prior probability. There is not a single way that can be fully objectively incorporate what really we know about the process before, assigning those parameters. So there is a subjectivity. In case of frequentist statistics, using the same tooling, having the same data, two frequentist scientists will always get the same results. In case of Bayesian statistics, having the assigned prior probability, each of them assigned by their own understanding of the process, they will get different results. And this is true, but it's not a bug, it's a feature. Because we, having ability to assign probability, we can evaluate our assumptions about the probability. We can see how our assignment of prior probability will influence, for example, the model operation. It will be relevant or not. For example, if you have a lot of data, unless it is very specific, it will not. It will be compensated by data completely. If we have a limited data, we can at least compute something, and what we can specific. But we assumed this. This was our assumptions. This is our limitation. We assume that this behaves this exact way. So the subjectivity happens, but as long as we are frank about it, we are honest with ourselves, we know that we assume something. Nothing is given, but we assume that certain aspects happen. Then our model, giving those assumptions, our model is gives this result. And then you can critique the models and critique the assumptions, but you know what to critique. So, for example, no, it's not possible that this parameter has a variance of, let's say, this parameter varies only by 1%. No, it's not possible. We know that it can vary by 50%. Okay, we know what to change in the model. We can add this extra knowledge, we can critique the model because this assumption was given. So, the prior knowledge is, but again, in case of, for example, when you have only one data point, frequentist statistics is rather, it's not in a good situation. For example, when you flip a coin, and you have only one result, you generally have a result that the coin should be only one result, right? You cannot influence the probability distribution to that. So that will assign that how likely is that the coin will flip on heads or tails or stand on the edge. You cannot assign that in frequentist statistics. You can, implicitly by assigning a Bernoulli distribution or binomial distribution, you can assign that there are two possible results. But again, if there are three possible results, that's a problem, and so you could have to do it a different way, and you cannot assign any preconception to the results. So for example, when we have a result of coin flipping, and there are two researchers that observe the results of flipping a coin and getting the results 10 heads, 9 tails, and 1 standing on the edge. It's very important to understand that if someone that is on Earth, let's say, knows how coins work, but if someone is from outer space, different dimension, let's go from fantasy worlds that haven't seen a coin before, just in 3 results. So for them, all could be equally likely. So they cannot distinguish what was really actual model, what is the sense of the model. So prior knowledge and critiquing the prior knowledge is very important. And of course, final aspect of in Bayesian situation is that everything has a probability distribution. If everything has probability distribution, so we say not only parameters, not only the data. The data is fixed, but what generated the data has certain randomization. So noise parameters are have probability distributions because we do not know what noise was. We can infer what was the probability distribution of the noise parameter. If we assume that noise is generated by random normal distribution, we still do not know the standard deviation. And this standard deviation in Bayesian parameter does not have a given value, it only has its probability distribution. And generally, there was a big war, and I think real war between frequentist statistics and Bayesian statistics. The people are being fired, they were being insulted, careers were broken, that's the subjectivity and stuff like that this is wrong, it's not a way to do science. But things happened that when we started being able to compute certain things in Bayesian statistics, because we will see very soon that it's not that easy, then it's shown that even subjectively it works very well. And it can solve problems that are not really solvable, like, for example, cracking codes or locating lost atomic bombs, or even such simple things like how to evaluate the rate of insurance for a young driver that hasn't driven yet. Classical statistics is not able to do that because that didn't happen yet. However, in case of insurance was the first place where Bayesian statistics moved from theoretical discussion, moved into practice. But they didn't call it Bayesian statistics because people didn't solve them, because there was very significant aspect of that. So this is a very good book, A Theory That Would Not Die. You can find it on Audible if you like to listen to audiobooks. I'm not sure, I haven't seen it in Polish, but maybe, perhaps there is. It's a history book, just a history book that starting from Thomas Bayes and Pierre-Simon de Laplace, how it moved through the history and how it's landed here and is being used very frequently. Especially in social sciences, medicine and biology, experimental sciences, diagnostics, decision support, all the situations when we are interested in the uncertainty and we want to predict on things that potentially haven't happened yet. So we want to know about stuff that is atypical, rare. Generally, from the basics of probability, Bayes' rule is a relatively simple formula. Because it's a simple formula which was actually devised by Laplace, because Thomas Bayes was a priest, and he constructed the conceptual idea for joining prior and posterior probability, but the practical computation was done by Laplace, as most of the basics of current probability was created by Laplace, who first created full Bayesian probability theory and then moved to frequentist because Bayesian required computation that was not feasible at that time. Generally, you can devise Bayes' theorem very simply from joint probability theorem, that the joint probability of two random variables can be expressed as the product of probabilities of one event and the second one conditional on the first one. And this, of course, can be flipped. So you can probability of the second one and the first conditional on the second one. It is easily, you can easily find it using the Venn diagrams, for example, how it works. And this can be relatively easily computed, giving us this formula that probability of one thing, customarily will be removed to t-test parameters, conditional on y, which are, again, we'll be using this as measurements, can be expressed as a product of prior probability of theta, the likelihood that y is consistent with theta, divided by the probability of y. And what is probability of y? Probability of y is the total probability of y for all possible values of theta, which If theta is a discrete event, it's very simple. However, if not, then we need to, then computation of this thing might be very difficult. And we'll today cover cases when such computation is simple, and we can do it, but usually we cannot. That is why, in practice, we will use often the symbol of proportionality here, and we'll focus on the numerator of the entire computation. Because as this symbol means that generally the denominator is not dependent on theta. So because it's not dependent on theta, we can assume that it's only some kind of constant that is irrelevant on the value of theta. It's only important on y. Why? Because we summed all theta out of the computation. And this means generally that our future, our knowledge about the future, or our knowledge that we can learn from the data, is a combination of what we knew before and what we've learned from data. So how the data corresponds to our understanding of the process and our knowledge about this process parameters. So relatively basic thing that you can, like, it kind of makes sense, right? That when we learn about something based on what we knew already before. And from the mathematical point of view, that was not that clear, which we discussed last time. Generally, we will need to focus on certain things that we will be using, in terminology that we'll be using during this course. We'll be focusing on both observables and unobservables. Observables are all the things that we can directly measure. Usually, observables will be the data or perhaps a structure of a process. Like, for example, if we know that the system has 3 water tanks, it has 3 water tanks, and this is fully observable in the model, probably even incorporated just directly. How unobservables, however, are all the things that we cannot directly measure. So, if we observe some kind of measurements, the actual phenomena that generates them is unobservable because there are some kind of uncertainty caused by the measurement process, right? Well, because we have sensor errors, we have survey problem reporting, we have inefficient methods of measurement, there are some kind of other aspects. So by the practice of what we'll be doing, we'll be focusing on parameters, denoted as theta, which will generally assume as a vector. So those parameters can be, when we write theta, we can assume that it's a multitude of parameters. It can be 1, it can be hundreds. Either way, it's a countable number of parameters. This is the generally even finite countable number of parameters. Data, which we denote by y, is something that we've measured, and we are using it to create our predictions, analysis, inference. In case if we are creating predictions, we will be using y with either with hat or with a wave, some kind of that, something that we predict using our available knowledge. Okay? There are few important assumptions that we will be using over time. Not all the time. There is one thing called independence, which is generally a rare event that certain things do not depend on each other. This is not the same as lack of correlation, because correlation can be created by multiple things, not really justified. You can find online nice examples of, for example, high correlation between number of Nicolas Cage movies and number of suicides. And like I said, correlation coefficients are like about 1, so it's as big as possible. But certain things are logically independent, that we know that they are not related to each other. And this is an important switch, because if something is logical, if we know that something does not depend on each other, is not related by itself. That's other thing is exchangeability. Exchangeability is a weaker thing, however, much more common in situation. We cannot, with much confidence, state something is completely independent. However, exchangeability is something that generally we cannot. We can, let's say, change, for example, order of data points, and nothing will change. So if we are considering individual experiments happening in different laboratories, they are exchangeable with each other. Sometimes, both in case of independence and exchangeability, we have conditional independence or conditional exchangeability. That means that because we know something, we can exchange those things together. Because we know about what's happening on those laboratories, we can just focus on the results because we've used the information about those elsewhere. The same with independence, that if we know something, that those things are completely unrelated if we take something under consideration. And finally, causal relationships. Causal relationships is something that we can analyze what causes something. So, for example, when we are doing diagnostics of a motor, we know that vibrations are being caused by the damaged bearings, and usually not the other route, right? So that's the damage inside the motor causes the vibration of the casing. So there is a causal relationship. We will often popular method of describing causal relationship is using directed acyclic graphs, which you perhaps met already. And using directed acyclic graphs, we can help ourselves to create our models, for example, to find out when adding certain variables will make more problems than justified. In our course, we will be focusing on the following tools that will, besides simple curve fitting or data fitting models, we will be using hierarchical models, and by extent, so the models that we have multiple levels of uncertainty, and the multi-level models when we have significant group relationships, that certain things belonging to different groups or combinations of those groups create certain effects. Like, for example, when modeling the favorite taste of ice cream, we can split our population depending on age groups and gender groups and the marital status, or having children or not having children, because parents usually have become accustomed to different things than children and stuff like that. So we have multiple groups that those groups, their dependence will have their own effects. We will be using utility distributions as a method of evaluating or propagating our predictions onto something. So, for example, creating a model of sales, we will be able to create from that a utility distribution of profits. So we would be able to generate, analyze the behavior of actual profits depending on the sales of individual products and their uncertainty by itself. And finally, some kind of model comparison methods, because we will be using and testing multiple models, and we will want to know how to compare one model with another, and how to avoid overfitting, and how to objectively verify how the model will behave when new data arrives, especially if we don't have that data yet. What is needed to be important? That everything is conditional. So whenever we create a Bayesian model, we have a set of assumptions. Those assumptions are those assumptions need to be explicitly stated, so we will be able to verify later why we make some decision one or another. Sometimes when we assign certain parameters or create some model, we assume something. The famous bumblebee that cannot fly because its mathematics says that the bumblebee is too heavy for its tiny wings to fly, failed based on the assumptions. The assumption that was used was that the sine of the angle, the angle of the wings is small enough that sine can be replaced by a linearization, the angle itself. Because the angles are too big, then using more complicated model, you could show that easily the bumblebee fly. But there was a confusion because the assumption was given, some kind of hypothesis was given. And our model, which we propose, is based on some kind of hypothesis, some kind of assumption, and all our inference based on that model is conditional of what we assumed before. So we won't be writing our assumptions explicitly this way in kind of model, but remember that everything is conditional on what we decided at certain initial levels. This is a bit complicated concept which I didn't have an idea where to put somewhere else in the lecture, but generally important aspect in what things that we'll be doing will be marginal distributions, or otherwise generally marginalization of parameters. Sometimes we are interested in one parameter and not the other. We want to know what kind of spread of certain value is, and we are not interested by the rest of the model. And using Bayesian computation, generally, we can do that. We can remove the unwanted parameters from our model. And we can do it analytically through rather complicated integration, but it can be done. And is often done in case of discrete parameters. When parameters assume discrete values, which for certain reason I will explain later, are very difficult to sample from, or more, well, it's difficult to sample that from models that have both discrete and continuous parameters. Discrete parameters by itself are very simple. Continuous parameters are hard but manageable. Combination of discrete and continuous parameters is very difficult, so that's why we often want to marginalize out the discrete parameters, discrete variables, and leave only the continuous ones. And this is the main use of marginalization, but not only, which we return in a brief. To sum it up, certain quote from Michael Betancourt, which I've mentioned before, that it is important that Bayes' theorem works everywhere. Bayes' theorem is a tool that works on the basis of transforming formulas. The important thing in Bayesian statistics is quantifying uncertainty using probability distribution and creating this learning system of what we knew before and what we added later and how it became created. So this is the most important things about Bayesian statistics.